So the most important bit of information is that exam 3 is on Thursday. And the topics for that are everything up through conservation laws. So any new stuff we do today is not relevant for this test. Okay, anybody have any questions about the test? And then there was one question about the weekly assignment that on number 3. So I'll give a hint or two about how to go with that. But if you have any other homework questions, daily assignments, I'd be happy to go through as much as you want. Weekly assignments, if you have questions about those, I could just give, help you get going in the right direction. So first, number 3 on the weekly assignment.
I don't think we have one yet.
Okay. Well, you have before though. So if you have any questions on any previous homework. Okay, so number 3, this guy. Okay. So here is so this question, it's sort of in multiple parts. It first asks you to calculate the lowest speed that this could be going at the top in order to stay in circular motion. This is number 3 on the weekly assignment. And that's going, so A and B are kind of all one part where you're just using circular motion and Newton's second law. And then after that, once you figure out the speed that it's going at the top of the circle, you can use conservation of mechanical energy to figure out what the speed is at the bottom of the circle. Once you figure out the speed at the bottom of the circle, you can use Newton's second law again. So you're going to use circular motion and Newton's second law for A and B. You're going to use conservation of mechanical energy for C. And then for D and E, you're going to go back to Newton's second law. And if you want any details about how to do this, it's very similar to example problems we've done. I think I did slightly different example problems in this class than in my Monday, Wednesday class, and I don't remember which ones I did.
Is this the one with like the carts that goes in?
Yes, this is very right. That's the one. It's very similar to the loop-de-loop thing where we're seeing how slow the cart can be going at the top in order to make it around. And even the math looks the same, surprisingly, because the direction of the cable force pulling on this ball is the same as the direction of the normal force of the surface pushing on it. And so the approach is basically the same. I think the one thing that we didn't do in those examples was at the end calculate the tension in the string at the bottom. But that's just going back to sort of standard circular motion stuff that we've done. Any other homework questions anybody has? Okay. Then I'm going to get into the new topic now. So the new topic is, it sort of goes by 2 different names, rotational kinematics or rigid body kinematics. In 2 quizzes so far, I've asked what the meaning of kinematics is. Anybody want to tell me what kinematics means?
You have like the amount of energy that an object has at a certain point.
It doesn't include energy. So kinematics is the study of the motion of an object without referring to the causes, without dealing with the causes. So there's no force, no energy, no mass. It's just what we've done so far has been velocity, position, and acceleration. And so now we're doing that kind of stuff, describing motion without the causes, but we're doing it for a new kind of motion. And we're treating bodies differently to start with. So a rigid body, this is, as opposed to a particle, which is what we've dealt with so far. A rigid body now has length dimensions. Remember, a particle we just treat like it exists at a single point. And because it has length dimensions, we can differentiate between parts of the body. So we can talk about which way is the left side or the top facing, that kind of thing. We couldn't do that with particles. So this allows us to consider the body's orientation. And we're going to see that there's a close relationship between rotational motion. That's this new thing that we're doing with rigid bodies. And circular motion, which we've talked about before. So circular motion, the thing that we've been dealing with, is the motion of a point or a particle around a circular path. The different new thing, rotational motion, deals with a change in a rigid body's orientation. Okay, so these two things are different. So let me first try to, help clarify what these two things mean. Okay, so circular motion, the thing that we've talked about before, is imagine that you're looking at me from above, okay, as I do this. So my body is basically like a point, like at the center of my body, you're looking down at the top of my head. And this is circular motion. You're just seeing that point move around in a circle, right? That's different than rotational motion. Rotational motion is this, okay? So instead of me moving in a circular path, some reference direction on my body is changing its orientation as time goes by, okay? And you can have a combination of both of those two things, and then you're dancing. That's called dancing. But rotational motion just has to do with the changing orientation, okay? So why are these two things related? So they're not the same thing, and you should try to keep these straight in your head. But what makes them related? So let's say that we have a rigid body, and it doesn't matter what its shape is. So I'm going to give it sort of a funny shape. Okay. And let's say that this rigid body, by rigid, I just mean that it's not bending or anything as it moves. Let's say that it's rotating about a hinge here. Okay. So this point here is a hinge. Okay. So this thing is rotating around. It could go either direction. Let's say it's going around counterclockwise like that. Make this a little bigger. Okay, well, notice that any point on this body, so let's say that we're tracking the motion of this point here. Okay, let's call this point A. Okay, as this body undergoes rotational motion, as the orientation of this body changes, this point A on the body moves in circular motion around that hinge. Are you with me on that? And that's true of every point on this body. So let's say so now let's say that the point B is this. Okay? That point B is also in circular motion around the center. Okay? So when a rigid body is in rotational motion, each point on the body is in circular motion. What kind of word is that? Circular motion around the hinge. Okay? Okay, so we're going to first talk a little bit about calculations involving rotational motion. And then we're going to come up with connections, equations that let us connect the rigid body motion to the circular motion of those points. Okay. In order to talk about rotational motion, I first have to define two quantities. So I first have to define angular velocity and we're going to denote angular velocity with the Greek letter omega, the lowercase Greek letter omega. That's like a rounded W. And angular acceleration. And we'll refer to that with the Greek letter alpha that looks kind of like an A or like a goldfish. So the first thing we have to do is define these two new things. So first, angular velocity. Okay, angular velocity is how quickly and in what direction an object is rotating. So could you think of a way to describe the speed that an object is rotating? Well, how much it's rotating, like how much something is rotated over some amount of time is how big an angle there is in the orientation of one sort of face of it, you know? So like, if I go from this orientation to this one, I've rotated 90 degrees, okay? And then you just want to know how much it's rotating for a given amount of time. So it sort of makes sense that the units for angular velocity would be an angle divided by a time. And in SI units, we're going to use radians for the angle. And the SI units for time is seconds, so radians per second. So, and we'll write it as rad per second. So the first thing this might make you concerned about is we haven't done calculations in radians yet this semester. Do you have to put your calculators in radians for this? No, you don't. So the first thing to notice is keep your calculators in degrees. It's never going to come up. So what is it in a calculation that makes you have to change your calculator from radians to degrees or whatever? It's just the trig functions, okay? And so we're never going to use these angular velocities or angular accelerations with trig functions, and so there's no reason to adjust your calculator, okay? We can break angular velocity into two parts, a magnitude and a direction. First, the magnitude. And you can think of that as just the total angle of change. Let's say the total angle of orientation change. Divided by the elapsed time. And then it also has a direction. And the direction is given by the plus minus sign. And so since we're doing all our calculations in the plane, there are only two directions something can rotate. It can either rotate clockwise or counterclockwise. Okay? So it seems pretty obvious, I think, to all of us that it would make sense to have clockwise be positive and counterclockwise be negative. And so in physics, we do it the opposite of that. So positive means counterclockwise. And negative means clockwise. So remember, it's the opposite of what you would expect there. So counterclockwise is like this way, clockwise is like this way. And let's just do a quick, simple example, kind of trying to make sense out of putting all this together. So let's say that a propeller rotates clockwise at 2,000 RPM. And we want to know what's the angular velocity in SI units. Well, RPM stands for rotations per minute. A rotation is one entire revolution to get the thing back to its original orientation. So how many degrees, well, no, let's think in radians. How many radians does something have to go through to return to its original orientation? 2 pi, perfect, yep. So one rotation is 2 pi radians. And then obviously 1 minute is 60 seconds. And so for the magnitude of this angular velocity, we can just do this as a unit conversion. We'll have to think about the sign afterwards. So it's going to be plus or minus. We'll deal with the sign in a second. 2,000 rotations per minute. One rotation is 2 times pi radians. And 1 minute is 60 seconds. So the rotations cancel, the minutes cancel. And then if you multiply out all these numbers, 2,000 times 2 times pi divided by 60, you get 209, hold on a sec, this is still going to be plus or minus, 209.44 radians per second. And now we just have to think about the direction. This is rotating clockwise, so is it positive or negative? Negative, so the answer is negative 209.44. And it's negative because this is clockwise. Any questions about that?
You can't choose clockwise to be positive instead.
No, and actually it wasn't really like somebody just chose. That's what it sort of is going to feel like in this class. It feels arbitrary, but it's all actually connected to math that we can't undo, like lots of complicated stuff that has to do with vectors and matrices and stuff. So, but for us, we just have to remember the rule of thumb kind of, you know. Okay, if you know the angular velocity of a rigid body, you can calculate the translational velocity, v, the velocity vector of every point on the body. And to calculate the magnitude of that velocity vector, So we'll say if we call the speed of the point capital V, and that's what we want to find is that, remember, the speed is the magnitude of the velocity, then that speed is equal to this Greek letter, that's a capital omega, times r, where that capital omega stands for the absolute value of lowercase omega, the angular velocity. And that r stands for radius, and that is the distance from the hinge to the desired point. Okay, so let's do an example with this. Actually, let's do two examples. So first, let's say that we have a board that's connected to, let's think of it as connected to the wall by a hinge. And let's say we want to know the velocity of this point. I'll call this point P. Given that the distance between the hinge and P is 0.75 meters. And as far as the rotation speed, say that we're given that the angular velocity is negative 10 radians per second. And we want to calculate the velocity vector of this point P. Okay. Yeah. Is that far enough? Okay. All right, so let's draw what's going on here. So I'm gonna just draw this circle first. And the hinge is always at the center of the circular motion. And the board is like this. And here's our point P. Okay, and we know that because the angular velocity is negative, this board is rotating this way. Okay, so now thinking about the velocity vector of that point P in terms of circular motion, what's the direction of that velocity vector? So we've done this kind of thing with circular motion quite a bit. This point P, it's not labeled P, but the one on the circle here, if this body is rotating around the circle clockwise, then this point P is following the circle clockwise, right? So what's the velocity direction of that point? Correct, exactly. So the velocity vector is tangent to the circle in the direction of motion, so we know the velocity vector is that way. And so that means the only thing we have left to figure out, to know the velocity vector, is to calculate the speed. And for that, we're going to use the equation that we're given. Okay, so we're going to use that the speed is equal to absolute value of omega times the distance from the hinge to the point. And so it's equal to the absolute value of negative 10, which is 10, times the distance between those two, which is 0.75. And so we get a speed of 7.5 meters per second. Yep.
I have a question. It might be a stupid question. Why can't we use like a cent and a ton, like how we did before?
Yeah, totally. We are going to do that. But remember here, we're still just talking about velocity.
Because like I'm kind of confused on like when to use what.
Okay. Well, yes. I mean, that is a perfectly sensible question. And we already know that the centripetal acceleration would be in that direction.
Yeah.
We don't know anything about whether it's speeding up or slowing down, so we don't know the direction of A tangential. We just haven't gotten there yet, that's all.
Yeah, because like I was wondering, like if you use a sen, like wouldn't you be able to use that to also calculate the velocity?
Remember, the centripetal acceleration is just a part of the acceleration. So it doesn't help you calculate the velocity. It only helps you calculate the acceleration. And so we will do that as soon as we talk about angular acceleration. Right now we're starting with angular velocity.
Because wasn't it like v2 over r?
Oh, I got you. Okay, yes, I got you. Yes, that's a very good question. Once we have calculated this speed this way, we could calculate the centripetal acceleration. And so yes, they are related in the way that you're thinking, but we don't have the other part yet of acceleration, so we're going to do that pretty soon. Yeah. So now that we have the speed, this velocity vector is in the negative y direction, so the velocity vector is 0, negative 7.5. Okay. Any questions about that? Okay, let's do another one. This one's going to trip you out big time. So get ready. Okay, so this time let's say that we have the body we're rotating is like this, like a sort of L shape or something. Those are supposed to be the same length. And I'm going to draw a circle. Well, I guess they're not quite the same length. Okay. And let's calculate, so the center is this, let's say that's the hinge. And let's say we want to calculate the velocity vectors of this point. I'll call that point A. And this point, I'll call that B. And you can see the two circular paths. Let's see. Okay, so you can see those two points A and B are lying on two different circles centered around the hinge. Okay, let's say that the distance from the hinge to A is, let's call that 0.5 meters. And the distance from the hinge to B, let's call that 0.8 meters. And let's say that the angular velocity of this body is positive 5 radians per second. And we want to calculate the velocity vectors of the points A and B. Okay, so the thing that we're going to see here that you probably wouldn't guess would happen, but it's sort of an important thing about the way rigid bodies move, is generally speaking, different points on the same rigid body have different velocity vectors, okay? And we're going to see that here. These velocity vectors are going to be different in magnitude and different in direction, okay? So a single body has the same angular velocity everywhere. The body just has one angular velocity. But every point on the body has a different velocity vector. Okay? Are you with me on that? Does anyone think that's, yeah, question?
When you say different velocity vector, you mean like the direction they're going in, or
It can be direction and magnitude. In this case, it's going to be both. If you want to picture that, I think one nice way to do it is, you know those carousel things that they used to put in playgrounds before all the lawsuits? The big iron things that spin around. So first of all, if you've sat on those before, you know the experience of, like, if you're close to the middle of it, sitting on it, you're not going very fast. If you're out on the edge, you're going a lot faster. So you know that feeling. So you have different speeds at the different parts. The other thing is, as far as directions, imagine this thing spinning around, and imagine reaching out and grabbing one of the handles as it spins around this way, okay? It's gonna jerk your arm that way, right? But if you're on the other side and it's moving in the exact same motion and you come over here and grab the handle, it's gonna jerk your arm that way, you know? So the velocity on this side of the carousel is this way, and on the other side is that way, even though it's the same body with the same angular velocity, okay?
so just spinning in different directions.
What?
Just spinning in different directions, right?
Yeah, the thing is spinning in the same direction, but different points are moving in opposite directions, yeah.
Oh, okay. Then if you're closer to the center, you're moving slower than if you're closer.
Right, yep. And I can tell you exactly why that is. In this equation for the speed, okay, if you can see that the speed is proportional to that distance from the hinge. So if you're at the hinge, your velocity is actually 0. If you're a meter from the hinge, it's whatever. If you're 10 meters from the hinge, it's 10 times as big. Okay, so let's do these calculations. We have these two circles. So there's the outer one, and then here's the inner one. Damn it.
But you were gonna make Mickey Mouse.
Okay, so that's good enough, I guess. So first of all, the point A is rotating around this red path. The point B is rotating around the green path. Which way are those points rotating around those two circles? And how can you tell? Well, we're given the angular velocity. That's where the information is. How do we know which way these are rotating? Yeah, right. It's positive. So does that mean clockwise or counterclockwise? Right. So it's going this way around the green circle and the same way around the red circle. Okay. And now for the green circle, we're looking at this point. So if that point B is moving counterclockwise around the green circle, what direction is its velocity? This is just going back to circular motion. What direction should I draw for the velocity? Down, yep. And then this is the point for the red circle. Which way is that velocity? Perfect. Okay. I guess I'll write this as the velocity of A and this is the velocity of B. And now we just have to calculate those speeds. So for the speed at A, that's going to be equal to the absolute value of the angular velocity, so 5, times the distance from the hinge to the point A, that's 0.5. And so the speed is equal to 2.5 meters per second. Okay? And now that we know the magnitude and we know the direction is in the negative x, we can say that the velocity vector of that point A is negative 2.50. Okay? Any questions about that one? Well, take a second and see if you can figure out calculate the velocity vector of that point. Okay, so for the speed of B, what's the magnitude of the angular velocity? Come on. It's the same for, yeah, it's always the same on the same body. There can only be one angular velocity for a body. And then what's the distance from the hinge to the point? 0.8, yep. And so the speed is 4. And now from thinking about circular motion, we had determined that this velocity is going to be in the negative y direction. So the velocity vector is 0, -4. Okay? Any questions about that? So we were able to calculate the velocities of both of these 2 points, and they ended up with different directions and different magnitudes. Okay, the next thing we have to define is angular acceleration. And we denote this with the Greek letter alpha. And this is how quickly the angular velocity is changing. The units for the angular acceleration are angle divided by time squared. And so that means the SI units are radians per second squared. And again, the direction positive means counterclockwise. And negative means clockwise. And now here's something that'll be familiar about this. If omega and alpha are in the same direction or have the same sign, would you guess that the rotations are speeding up or slowing down? Yep. So the rotations are speeding up. And then if they're opposite directions, then that means they're slowing down. The rotations are slowing down. Any questions about that? All right. So remember when we talked about angular velocity, we did these direction things, and then the next thing we did was come up with a relationship between the angular velocity and the velocity vector. Okay, now we're going to do a similar thing for acceleration. So if you know the angular acceleration for a rigid body, you can calculate the tangential acceleration vector for any point on the body. And this formula is going to look very similar to the last one. So we're going to say, if A tan without the vector symbol is the magnitude of the tangential acceleration vector, then the formula says A tan is equal to capital alpha times r where capital alpha is the absolute value. I'll just write it in math symbols. So capital alpha is the absolute value of the angular acceleration, and r is the distance from the hinge to the point. Okay? Yeah.
Why wouldn't it be just the speed of the spin, not the acceleration?
To calculate the tangential acceleration? Well, the speed that it's spinning will let you calculate the velocity. It'll let you calculate basically how fast the point is moving, but you need to know how quickly those rotations are changing in order to calculate the acceleration. So, I mean, just think of both of these, the tangential acceleration and the angular acceleration are both telling you something about how much the speed is changing. So it kind of makes sense that they would be related to each other. Yeah.
Tangential acceleration is not the same as parallel acceleration.
Okay, so it is the same. It's just that tangential acceleration is we only call it that for circular motion. Yeah, it's the parallel acceleration, but we just give it its own name for circular motion. It'd be nice if we didn't have to do that, but people have just already come up with that terminology.
Yeah, when we were talking about at the point where if a point's at the top or bottom, it has 0 tangential versus the sides, and it has up through and down.
Say that again. We were talking about.
At some point we talked about if
Oh, yes. Okay, right. I know what you mean. So that just in the specific case of an object swinging around on a string.
with gravity acting upon.
Yeah, right. Then at the top and bottom, at those instants, the speed isn't changing. Everywhere else it is changing based on whether it's rising or falling. Yep.
So in like a situation where the speed at which it's spinning is the same, but it's still positive, but the acceleration isn't like changing, you can't tell that acceleration tangent.
If there's, okay, so.
If you're still spinning, you know the speed at which something is spinning.
Yeah.
You can't tell the acceleration tangent because it's still going
Oh,
in a circular path.
okay. So if all you know is the speed that it's spinning, you can calculate the centripetal acceleration from that, but you can't calculate the tangential acceleration from that. But yeah, you guys are right on it with the centripetal acceleration thing, because that's, so now we're going to get into calculating the total acceleration, and we're going to have to use what we know about centripetal acceleration along with this. Okay, so let's do an example. And let's say we have a board, and the hinge is here. And we want to know the velocity and acceleration at this point P. So let's say that we know that the angular velocity is 10 radians per second. The angular acceleration is negative 20 radians per second squared. And we want to calculate V and A at that point P. Okay? So really a lot of this, most of this is just thinking about it in terms of circular motion like we've done before. But then we're also using those two new equations we have to relate angular quantities to our old quantities. So let's say, okay, here's our board. The hinge is at the center of that circle. Here's our point P. The angular velocity is positive, so is this rotating clockwise or counterclockwise? Counter, and so which way does the velocity of this point go? Up, yep. So the velocity vector is this. Now there are two ways to think about the direction of the tangential acceleration. You can think of it in terms of these two being opposite, meaning it's slowing down, okay? So if it's slowing down, is the tangential acceleration in the same or opposite direction of the velocity? Opposite. So, so our tangential acceleration is straight down.
Does it matter if you label it tan or parallel?
I guess I don't care. Yeah, but other people, I mean, when in the many times in your life when you'll be having conversations with people about circular motion, they'll talk about it as tangential acceleration. And then the centripetal acceleration always points toward the center of the circle. So now we have the directions for these three things. And now we can just use those equations. So the speed of that point P is equal to absolute value of the angular velocity.
Professor, how
Yeah.
do we know it slowed down?
Because the angular velocity and angular acceleration have opposite signs. Oh, I forgot to give you a length between these. Let's say this is 0.5 meters. Pretend I told you that. You can't do this problem without knowing that. Okay, so the speed is 10 times 0.5, so 5 meters per second. Now we know the velocity is in the positive y direction, so the velocity vector of that point is 0, 5. Now we can use that speed that we just got, like you figured out a long time ago. We can use that to calculate the centripetal acceleration magnitude. So this is equal to v squared divided by r. So 25 divided by 0.5 is 50. That's in the negative x direction. So the centripetal acceleration vector is negative 50, 0 meters per second squared. And then now we have to calculate the tangential acceleration. The magnitude is equal to 20 times 0.5. So that's 10 meters per second squared. We know that that's in the negative y direction, so the tangential acceleration vector is 0, negative 10. And so now the last thing we're asked for is the total acceleration. That's just the sum of the two parts of the acceleration. And so that's -50, -10. And so one thing you could do with this bit of information is if, like for example, if this was part of a machine and you had some kind of microchip or something that was at this point here, you might want to calculate that acceleration to see how much force you had to apply to hold it in place. Or if you knew some amount of acceleration would damage it, then this calculation would let you figure out those things. Any questions about those? Okay, I want to do one more thing, just give you a short little table, and then we'll stop for today. So the old stuff, velocity vectors, acceleration vectors, that kind of stuff, I'm going to call that translational information. And the new stuff I'm going to call rotational. And I just want to sort of list out all the things that are kind of the same about these, that are analogous between the old stuff and the new stuff, okay? Because you really don't need new brain space for a lot of this. It works kind of the same way as the old stuff did, okay? So with translational stuff, we had a velocity vector. With rotational, we have the angular velocity. In translational, we had an acceleration vector. And actually, let's specifically say we had a tangential acceleration vector. With rotational, we have an angular acceleration. With translational motion, if the velocity and the tangential acceleration are in the same direction, then the thing is speeding up. With rotational, if omega and alpha are in the same direction, the thing is speeding up. With translational, if the velocity and tangential acceleration are in opposite directions, the object is slowing down. With rotational motion, if the angular velocity and angular acceleration are in opposite directions, the rotations are slowing down. And then the last thing, and the thing that we're sort of heading towards, is with translational motion, we remember that F net is equal to mass times the acceleration. With rotational motion, we're going to see that there's kind of a rotational version of force called the torque or the moment. And if you add up all of those rotational forces, those torques and moments, that's equal to a rotational sort of mass times the angular acceleration. And so it works just like Newton's second law does, but this governs rotational motions and this governs translational motions, okay? And all of these pieces have kind of the same meaning. This moment is like a force, but in rotations. This moment of inertia, I, is like a mass, but with rotations. Okay, so remember, don't make new brain space for all this stuff. Use your old memories, and it'll, like you already have this stuff in your brain. What? They mean, yeah, these mean, this stuff all means for the motion of particles. This stuff all means for the rotations of rigid bodies, but it just notice how similar it all looks. Okay, that's all.